got here an idea. I got an idea. Check it out. All right, we're gonna be talking about sticky pads. I got an idea for a sticky pad. Basically, what I'm picturing is a pad like right here, but kind of like Legos. This little one is this one that would have notches. So go like that. Have little notches that come out of it. It's like three-dimensional too. So it'd have notch, 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 notch going down, and notches all on the side, right? On the other side, you have little holes or indentations in which the notches can fit in. And then you also, I'm going to get to it later on, but you could also potentially superheat or super cool it, or just heat it or cool it. Doesn't have to be super, but you could just make possibly, depending on the materials, if it's like metals or something like that, more durable, you're going to need more heat. So you might need a superheat or super cool it. But with more basic materials, things that are a little bit more malleable, you're going to have an ability to maybe not have to use as much heat or cooling in order to get it to expand or contract. But you can use that expansion and contraction, like say the expansion, like once you have it plugged in, to make each of the little notches expand and then fit more snugly into the hole or indentation on the second pad. I have possible shapes here. I was trying to do a little bit of research to see what the most what the best shape for structural integrity would be. And according to Gemini, from what I'm finding, is a square or a flat surface, but I don't really think it's completely understanding my question. So here, I'll read this and then I'll get over to what I got from Gemini. So possible shapes, I included a square, rectangle horizontal, rectangle vertical, hexagon, octagon, trapezoid, inverted or upright, triangle, inverted or upright, dome, inverted or upright, oval, horizontal, oval, vertical, or a circle. And question I was proposing is, which shape or structure is best for distributing downward force for maximum structural integrity? We have G, gravity, exerts a downward force that we must meet with the normal force on top of that with any additional resistance, like say from the notches, that we might be able to supplement the normal force with. The sticky pad is a double-sided adhesive mechanism to help attach and secure one object to another object. Say one object to another object, object to a wall, etc. No need for nails, screws, or other tools that can cause potential damage. I have a diagram here of a couple of them, a couple of designs for pads. One's a square, one's a circle. I did the height for both of them as 2 inches just to basically create a visual depiction that demonstrates that, yes, a circle indeed has less surface area if you have a 2-inch diameter. So if you're fitting it into the same space, like say same region, the circle is going to take up less of the surface area than the full square, and probably going to be able to have more holes and notches than the circle would as well. And another question proposed here, which I think I proposed to Gemini, we'll answer in a little bit, is do more holes, 1, add surface area for additional friction to help keep pad 1 attached to pad 2, or 2, decrease structural integrity due to less surface area on the main or largest side or face of each of the pads. And then here, here's the point that I was kind of covering, I was going to get to, is for heating, for additional friction or support, heat the pad with the plugs or notches attached to it so that it expands and presses up snug and tight against the pad with the holes or indentations on it. And so I drew a diagram here, which the not heated one, the one with the notches are a little bit smaller. So it's contraction via cooling. And then those were about, just threw an arbitrary number out, about 0.1 inches for each of the little notches. Could be smaller, could be bigger. Then the heat allows it to expand, and then the notches grow to maybe about 2 inches in diameter each, or 0.2 inches in diameter each. So either way, arbitrary number again, but still larger than before and fitting more snugly within the holes of the other piece. All right, so let's go to what Gemini was talking about, so we can do a little bit more research, get a little bit more facts and figures for what we're trying to do here. So I basically asked, if we were to develop a small pad to attach to a wall and I wanted it to be able to support as much downward force as possible, what should the shape of the pad be? Should it be flat on some sides, round or pointed, Also, should there be holes in one of the pads so that whatever is being attached to it can fit components into the pad like a plug and an outlet? How many holes should there be? Do more holes help increase the amount of friction between the pad and the attaching material, or does more holes compromise the structural integrity of the device? Gemini responds, the ideal shape for a wall-mounted pad designed to support maximum downward force is a flat, solid rectangle or square. This shape provides the largest possible surface area for friction against the wall, which is the primary force counteracting the downward pull. Shape of the pad. A flat, solid surface is optimal because it maximizes the contact area with the wall. The downward force or shear force is resisted by the frictional force between the pad and the wall. The magnitude of the static frictional force, F underscore F, is directly proportional to the normal force, F underscore N, pressing the two surfaces together, and the coefficient of static friction, mu underscore S. So there's an equation here that says F underscore F equals mu underscore S times F underscore N. In this scenario, the normal force is generated by whatever is holding the pad to the wall, for example, glue, tape, or nails. By maximizing the surface area, you can distribute this normal force more effectively and ensure the frictional force is uniform across the entire contact surface. Round or pointed shapes would reduce the contact area, thereby reducing the maximum possible frictional force. Holes in the pad. Adding holes to the pad would compromise the structural integrity and decrease the total frictional force. Decreased friction. Each hole reduces the available surface area for contact with the wall, which directly lowers the maximum possible frictional force. Think of it like this. If you have a 10-inch by 10-inch pad, the total contact area is 100 square inches. But if you punch a 1-inch hole in the center, you reduce the contact area to 99 square inches, and thus the maximum possible friction is also reduced. Compromised integrity. The presence of holes creates stress concentration points. When a downward force is applied, these points will experience higher stress than the rest of the material, making it more likely for the pad to tear, break, or deform, especially around the edges of the holes. For a simple wall pad, it is generally better to have a single, solid piece of material to distribute the load as evenly as possible. Therefore, for a simple wall pad designed to maximize support for a downward force, you should avoid adding holes. Instead, the material being attached should be designed to mount directly to the solid surface of the pad. I followed up by asking, what if the holes on pad 1 are filled in by plugs on pad 2, which can increase the surface area of contact and increase friction, thereby increasing the amount of resistance to downward force? Am I correct? And then I'll just ask him, is this accurate or correct? Gemini responds, no. Adding plugs and holes don't necessarily, this is where I think it may have misinterpreted my question, because I wasn't thinking about just a hole in here and then like holes and attaching to holes. I'm talking about holes and plugs attaching to the holes. And then I would think that something flat would have less surface area than something like that. So you're increasing the surface area, say from like 10 inches, arbitrary number, to like, and then all this surface area going along the sides, add this, plus 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 this, etc. And you go down the list, that's going to be way more than 10 square inches. Again, arbitrary number. But we'll see what Gemini says, because I think it misinterpreted the question slightly, but I think I do clarify a little bit later on the next question I ask. So anyway, let's see what Gemini has to say. Where was I? So no, adding plugs and holes doesn't necessarily increase the friction. It can actually make the design weaker. While the plugs might add some friction on their own, a solid flat surface is generally the best design for maximizing resistance to downward force. Why holes aren't ideal? The core issue is that creating holes removes material from the pad. Even if you fill those holes with plugs from another pad, you've now introduced two potential failure points: the interface between pad 1 and the wall, and the interface between pad 1 and the plugs. The downward force can cause the plugs to shear off or the material around the holes to tear. This is because the holes create stress concentration points where the stress on the material is much higher than the surrounding area. The friction fallacy. The idea that plugs increase surface area for friction is a common misconception. The total amount of friction between two surfaces is primarily determined by the normal force pressing them together and the coefficient of friction of the materials. While a larger surface area can help distribute the load, the total frictional force doesn't inherently increase just by adding more surface area in the form of plugs. A solid, flat pad provides the largest possible continuous surface area for friction with the wall, which is the most effective way to resist a downward force. A better alternative, instead of using holes and plugs, a superior design would be to have two solid, flat pads that are held together by a separate mechanical fastener, like a bolt or a strong adhesive. This design maximizes the contact area between the two pads and between the pads and the wall without compromising the structural integrity of either piece. I followed up by saying, so what you're saying is that the flat surface would, I may have misinterpreted Google Gemini too, so just bear with me. So what you're saying is that a flat surface would have more friction than a coarse surface where parts of one pad can be inserted into the holes or hollow or indented spaces of the other pad, increasing the amount of surface area between the two pads. Looking at the two pads pushed together, I would think that a more coarse surface or a solid piece with notches would fit into another solid piece in which the notches fit snug or were heated to expand and apply more pressure to the walls of the holes that they are being inserted into. Gemini responds, what you're describing, a coarse surface area or a coarse surface with interlocking notches or a plug and hole system is a great way to increase mechanical interlock, but not necessarily static friction in the way you might think. For resisting downward force, a flat, solid surface is generally superior to interlocking design for a simple pad. Understanding the difference, friction versus interlock. Friction, this is the force that opposes motion when two surfaces slide against each other. The maximum static friction force is directly proportional to the normal force pressing the surfaces together and the coefficient of friction of the materials. For a wall pad, the friction resisting downward pull comes primarily from the pad's flat, solid surface pressing against the flat surface of the wall. Maximizing the flat, continuous surface area maximizes the potential for this type of friction. Mechanical interlock. This refers to two objects physically hooking or locking into each other. The interlocking features like notches, plugs, or grooves prevent sliding by creating physical barriers. While this is extremely effective at resisting shear force, it is a different mechanism from friction. A plug and hole system relies on both friction and mechanical interlock. The friction comes from the surfaces of the plugs rub against the surfaces of the holes. Bingo. Okay, I think you're onto it. I think you got what I'm saying. Okay, so it did understand that question, the last one at least. The interlock comes from the physical presence of the plugs, preventing the pads from sliding past each other. The problem with a plug and hole design. While an interlocking design might seem more robust, it introduces several weaknesses that make it less ideal for a simple wall-mounted pad. Stress concentration. The edges of the holes and the bases of the plugs are points of stress concentration. When a downward force is applied, these areas bear the brunt of the load. This makes the material around the holes and the plugs themselves more susceptible to cracking, tearing, or breaking under stress. A solid, flat pad distributes the stress evenly across the entire surface, making it less likely to fail. Manufacturing and fit. Achieving the snug fit is very difficult in mass production. If the plugs don't fit perfectly into the holes, the interlocking will be weak. If they are too tight, they can be difficult to assemble or even crack the material. A flat surface, by contrast, is much easier to manufacture and provides a consistent, reliable contact area. Expansion and pressure. While heating a plug to expand and create more pressure sounds good in theory, it's an advanced engineering technique not suited for a simple wall pad. This process could deform or damage the materials and is an unnecessary complication for this application. In summary, for a simple wall pad, a solid, flat surface is the best choice. It provides the largest, most consistent surface area for friction against the wall, avoids the structural weaknesses of holes and plugs, and is the most reliable design for resisting a simple downward force. All right, solid. Gemini. Oh shit, I didn't mean to unlock it. Sorry. Like. Gemini for the win. All right, so we got sticky pads. That's all we got. That's all I got for sticky pads right now. So cool. Hopefully that helps. Hopefully somebody can use that because I'm just gonna be pumping out ideas. I always used to be like, I'm gonna hold on to these ideas because I don't want anybody stealing them. They're great ideas, and I don't want anybody else making out of money when I could like do them myself. And you know what? I've been saying that for the last like 10 years, and I've just been holding on to those ideas, and they've just been sitting on my shelf. So I'm just gonna go ahead and let them out. And I mean, if I do stuff myself, great. If somebody else picks it up and wants to do it, also great. I mean, contact me. But also, I think that's really great if somebody wants to go ahead and use that to be able to benefit the world, be able to create technologies that can help people to, whether it be for their health, whether it be for their entertainment, whether it be for their professional growth, and or or helping them develop relationships or whatever it might be to make whatever it is you're trying to do easier, more efficient, better, more entertaining. I'm just basically going to start pumping out ideas so that way maybe somebody can go ahead and take them. And I got a lot of improvements that I have ideas for, a lot of modifications, rectifications, um, a lot of complex ideas, a lot of dumb little ideas, but the only ones I save are the ones that I think are pretty good. But at the same time, it's been a while since a lot of them have been sitting over there. So by now, since I've learned a lot more, I could be going through some of these and be like, that one's not so great. But for the most part, I'll probably say like at least I can comfortably say at least half of them are genuinely decent. I'd say 7 or 8 out of 10 are like at least interesting. And then there's probably maybe a couple that I might be tossing out. But that's why I'm cycling through. That way, if you guys can see them, I can re-see them, edit them, and work on them, do whatever I want instead of them just sitting right there on a shelf collecting dust. So, trying to do this in a way where people can actually use it. And all right, cool. That's it for sticky pads. Go ahead and end that, and looking forward to seeing you guys and sharing some more ideas later. Thank you. We're doing work.